Hey there and welcome. So today we're going to do something that sounds a little crazy. We're going to take a circle, one of the simplest shapes you can think of, and we're going to unroll it. And in doing that, we're going to reveal one of the most important, most fundamental curves in all of science. It's going to be a fun ride, so let's get started. Okay, so I want you to imagine something for me. What if you could actually take a circle, pick a point, make a little snip, and just lay it out flat like a piece of string? What kind of shape would you get? It sounds like a simple question, but the answer is the key to, well, pretty much everything we're about to cover. All right, let's dive right in. We're going to start with something you probably already know from trigonometry, the good old unit circle. And we're going to use it to uncover something totally new and fascinating. So, first, a quick refresher. Remember, as a point travels around the unit circle, its height, that's its y-coordinate, is what we call the sine of the angle. It goes up to a max of 1, down to a min of -1, and back again. And that simple up and down motion, that's literally all the information we need. You know, the process here is actually super simple. All we're doing is tracking the height of that point as it moves. For every angle we pick, we find its sine, that y value, and we just plot it on a totally new graph. The x-axis on our new graph is just going to be the angle itself. So what happens when you do that for every single point all the way around the circle? Well, you get this. The sine wave. It's this perfect, smooth, repeating curve. This is literally the circle's vertical journey, just unrolled and laid out flat. Pretty cool, right? Okay, so we've built the wave. Now, let's break it down. Just like any living thing, every sine wave has its own anatomy, its own DNA. And once you understand these key features, you've pretty much mastered how these waves work. Now, what's really interesting about this slide is how it lays out the wave's core identity. You've got the amplitude, which is just how high it gets from the middle. You've got the period, which is how long it takes to complete one full cycle. Then there's the midline, that center line it oscillates around. And of course, its highest and lowest points, the crust and the trough. All right, let's talk about amplitude. Remember our unit circle? Its radius was 1, right? That means the point never went higher than 1 or lower than -1. So it makes perfect sense that the amplitude of our wave, its maximum height from the center, is exactly 1. Think of it like the wave's intensity or power. Okay, next up, the period. This is just asking how long does it take for the wave to do its whole thing before it starts repeating? Well, it took one full trip around the circle to make one full wave. And the distance around a unit circle is its circumference, which is 2 pi. So the period, the length of one cycle, is 2 pi. And what's so cool is that the wave has this super predictable rhythm. It always follows this pattern. It starts at 0, goes up to its max, comes back down to 0, drops to its min, and then returns to 0. This simple little 5-point pattern, that's your golden ticket for graphing any sine wave fast. All right, theory's great, but Lynn's actually put this to work. We're going to use that 5-point pattern to quickly map out one full cycle of the most basic sine wave there is, y equals sine of x. Okay, check this out. First, we know the period is 2 pi. Now, since our pattern has 5 key points, that means each important moment is a quarter of the way through. So we just divide 2 pi by 4, which gives us pi over 2. Then you just count up by that amount for your x values, 0, pi over 2, pi, and so on. Finally, you just apply our pattern for the y values, 0, max, 0, min, 0. And boom, there you have it, the 5 key points you need to draw the wave. Okay, I've got to give you a heads up here. I'm about to save you from a ton of frustration. This is a super common mistake I see all the time when people first start graphing trig functions, and it's all about what units you're using. Just look at the difference here. On the left, with radians, the x-axis lines up perfectly with the wave's period of 2 pi. Everything just fits. It looks beautiful. But on the right, if you accidentally use degrees, oh man, it's a total disaster. You're basically telling your calculator that the wave ends at an x value of 360, which means it tries to cram 360 full cycles into that space. It just becomes an unreadable mess. So here's the bottom line, the one thing you really need to remember. When you are graphing trig functions, you have to use radians. Always, always, always. The mouth of the sine wave is just baked into the geometry of the circle, and circles speak in radians, not degrees. So you might be thinking, okay, this is kind of neat, but why does it really matter? Is this just some abstract math thing? Well, let me tell you, it's not. This wave is literally all around you right now. In fact, you can hear it. Believe it or not, every pure musical tone, like from a flute or a tuning fork, is actually a pressure wave moving through the air that looks exactly like the sine wave we just drew. It's not a metaphor, it's the real deal. So, get this. When you strike a tuning fork that's tuned to the note A, it vibrates back and forth 440 times every second, creating a perfect sine wave in the air. The amplitude of that wave, that's how loud the note is, and the period, or how close the waves are together, that determines the pitch. It's a direct connection. This is the math behind music. Which brings us to a really amazing final thought. If one simple, perfect sine wave creates one pure note, what kind of incredible, beautiful math must be hiding inside a full symphony orchestra with all its instruments combined? It's wild to think that all that complex and beautiful music, it all starts with the simple, elegant act of just unrolling a circle.